So, Shaun, welcome to the podcast. Absolute pleasure to have you on. How are you?
I'm great, thank you. Yeah, it was great to be here. Thank you very much for asking me to come along.
No worries. Absolute pleasure. Appreciate the support as well, and obviously your time. So, we are going to be talking all things quantum computing today, which I'm looking forward to. I guess for anybody tuning in who doesn't know you, not aware of your background, do you want to give a bit of an intro of who you are and what you do?
Yeah, of course. So my name is Shaun Geaney. I'm a quantum computing specialist at Standard Chartered Bank. Prior to this, I did a PhD at the National Physical Laboratory, which is in Teddington in the UK, where I was doing research into sort of defects that exist in qubits, which we'll get onto later. And then from there, I went to work for a quantum computing startup where I used to build quantum computers. And now my role is effectively programming quantum computers. So I feel like I've done almost the full stack in a way, and when it comes to dealing and working with quantum computing.
Awesome, yeah, and hopefully we'll get into that kind of transition a bit later on in the podcast because it's certainly an interesting one. Um, so, obvious questions, super high level. People are probably kind of wondering why is a quantum computer different to a normal computer? Are you able to explain, I guess, at a fairly kind of layman's terms level, what the key kind of differences are?
Yeah, no, absolutely. So your audience may or may not have come across this idea of you have in normal computers these bits, these ones and zeros, whereas in a quantum computer you still have those, but you effectively have what's called a very technical word, but it's called a superposition, but it just means you can be a mix between those states. And by exploiting that property and other inherently quantum properties, you can, for certain types of problems, gain exponential processing power. So the way I like to think of it is it's almost like a new tool, essentially. So we have normal computers like our laptops, say, or our desktop computers. Then you can take that up a scale to, say, data centers, which are much more powerful at processing more information and networking between all different applications around the world. And quantum computing are really good at certain problems like optimization, simulation. There's going to be a lot of impacts on AI and machine learning as well. So it's a fundamentally new type of technology built differently from the ground up, and there's many different ways you can build them as well. And by applying this new type of weird science and physics, you can hopefully exploit some new computational power that we've never seen before.
Amazing, and it's certainly an interesting topic. QC, I think it's along with AI. There's a bunch of subtopics, and I mean, quantum's a topic in itself. But yeah, again, hopefully we can come on to how that might potentially impact the kind of AI world a bit later on. So I guess interestingly, I'm quite keen to understand how you got into quantum technology and ultimately where you got your start.
Yeah, no, that's a great question. I sort of kind of fell into it by accident, really. So I did my master's in physics in the University of Manchester, and I was enjoying the course, but nothing had really sort of like really captured my interest at that point. And it was just by chance in my fourth year there was a module, not even in the physics department, in the computer science department called quantum computing. I was like, oh, what's that about? This sounds weird and interesting. So I did that course, ended up really enjoying it, and then because that was like the last semester in university, I already had a job lined up as a software developer. So I ended up doing web development for a year before deciding, actually, no, I want to go back and do a PhD. So I did some research online, found a few PhDs that I applied for, and I ended up getting one that was between Royal Holloway, the University of London, and the National Physical Laboratory, which is it was sort of like a joint PhD between them. And I started that PhD in around, oh God, when was it? 2016-ish, 2017, and it was essentially a thesis or a very experimental PhD, very hands-on, where I was looking at individual qubits, which are these ones and zeros that we were discussing earlier, as you physically build them on some sort of chip. But some of the problems that they have is they have inherent defects in the way that they're made, just because of how the atoms place themselves on chip, or certain defects can appear. And the key problem was no one knew exactly what these defects were. You could measure their effects on these qubits. They sort of caused what's called decoherence, which basically a technical term that means they sort of lose their quantum properties over time, which is not an ideal thing you want if you're trying to process quantum information in your quantum computer. So I was trying to build a microscope that was going to detect an individual one of these defects for the first time. And it was quite the engineering challenge I had to build, because you need to have these systems to be very isolated from the environment. So I built this whole like suspension system to try and measure these defects, and you have to have all these different types of microwave equipments that use the sort of same technology that you do in like radio signals and telecoms to interrogate the response from your qubits and so on and so forth. And that gave me a lot of technical hands-on expertise. So after the sort of 4 years when I did my PhD and I passed my viva, I then got an offer a company called Oxford Quantum Circuits, which is a startup in the UK that is building quantum computers. And I was working for them for about 2.5 years, where I was doing all sorts of things as you do in the early days of a startup. But I was primarily focused on building the sort of enclosure where what's called the QPU, which is the quantum processing unit, equivalent to that sort of CPU and GPU, but for a quantum computer, where the
Yeah.
housing in which that sits, which has, you would think that would be a simple problem to solve. There's a lot of things you've got to take into consideration, like its thermal conductivity. It's got to get cold quick. It's got to be isolated from the outside environment. It's got to allow only the signals you want to get in, and it's not got to be able to have almost the equivalent of an echo chamber. You have to think of ways in which you mitigate those effects and so on and so forth. So I was designing a lot of that, and also a lot of the cabling that goes in that speaks to the qubits directly as well. And after doing that for a while, again, another sort of like luck chance, I saw an opportunity at where I am now at Standard Chartered to now work on the sort of software side. So you get to start writing programs and machine learning algorithms for quantum computers. And I thought, well, let's try it. It's something I've never done before, see if I can. So I went for the interviews. I got the job, and that's what I've been doing for the past about 2.5 years now. So I've been transitioning very much from hands-on hardware type of work to sort of programming quantum computers and thinking about how you'd use them for solving actual real-world applications in a bank now as well, which is an exciting and difficult transition.
I can imagine, but I guess just reading between the lines there, that kind of journey that you've been on the hardware to the software side, I guess that's probably teed you up quite nicely, has it? Because I mean, understanding the hardware at that level versus where you are now on the software side, it probably gives you maybe a better understanding than most. Is that fair?
Yeah, I think it gives you certainly a different sort of lens in which to look at it, because
Yeah.
one thing you don't have to consider when you sort of write programs on your computer now in Python or C++ or whatever you choose to write your code in, you don't really have to think about the bits at an individual level. You don't have to think about how you program this 0 and 1. Sure, you might have to think about in sort of more languages like C++ how you allocate memory and things like that, but you don't have to think about, okay, I need to program this 0, this 1, and this individual, and program by the bit. But in quantum computers, because there's still, say, of the order between a few dozen to 100 qubits, you are basically applying individual gates to individual qubits, essentially. So you really have to think how you place those in what's called a quantum circuit, which is just another way of saying a quantum algorithm. And there's certain techniques you use on the hardware side that you can sort of exploit in the software side. So a good example is there's something called a Z gate, which is almost like a bit flip, essentially. But you can almost do that a cheeky way for free in hardware. So it means you don't get these problems by when you apply another gate, you don't have to worry about the extra noise or the loss or the decoherence that we mentioned earlier. So it's sort of almost a cheeky free gate that you can get, and you can say, okay, I can put that in, but it doesn't affect the overall length of my algorithm in a sort of real world terms, because the more gates you had in your bigger algorithms, the more decoherence you have. So by having that extra understanding of what's going on down at the bare metal, so to speak, you have ways in which you can think about of making your algorithms maybe a tiny bit more efficient.
Nice. Yeah, I guess it's all these kind of under the hood type methodologies and kind of tips and tricks that can potentially obviously help you on the software side. So yeah, that's super insightful. So I guess kind of being in a super niche technology area, working as you put it earlier, wearing loads of hats, working in a startup environment, going from that startup to the kind of large kind of corporate environment, how's that kind of transition been?
Yeah, it was a very stark transition. So like you said in the startup, you sort of do a bit of everything. And I remember there's a story of how it sort of exemplifies how we have to do a bit of everything in the startup. Because when I first joined, I think I was number 7. Then we moved to a bigger premises to sort of build out the startup at the time. There was probably about a dozen of us, if maybe a bit less at that time. But overnight, at one point, we have cooling waters that help cool the sort of machinery that helps keep the quantum computers at the ultra low temperatures that they are. And there was just a burst pipe, and there's no maintenance team you can rely on. You just got to effectively become a plumber at that point. You've got to get on your hands and knees, wipe up all the water on the floor with some blue towels, and then find the source of the leak and try and seal it there and then. And if a wire breaks or goes cold and snaps because of the temperature change, you've got to find that and dissect it yourself. So then one day you become an electrician, and then the other day there's okay, we need to think of ways of, maybe we need some new software that sort of interrogates these qubits in some way. Okay, the next day you're a software engineer now. So you sort of flip between roles very quickly, and there's not really a process to do things. You get faced with a problem, you sort of fix it. Whereas when you go to a much larger organization, those processes are already in place, and you're there to do that one thing. And there's a whole support network and team. Like there's an IT team if your laptop breaks, or someone else is fixing the plumbing if that breaks, for example. So it was a real sort of stark change in terms of going from like a jack of all trades to being able to focus on your specific task and how that adds value to a much larger organization as well. So it really is a stark change, but it was a fun one nonetheless. So it's still being exciting today when you get to say to other people, especially in a place like a bank, that you're working on this quantum computing technology, and people get very excited and ask what that's all about.
Yeah. Do you do you have a preference in terms of kind of being super busy in that kind of smaller environment, as you say, wearing the different hats versus being, I guess, more specialist and almost being, I guess, quite consultative? Because I would imagine with quantum, or certainly QC within financial services, it's very much kind of in its infancy, right? So there's probably a ton
Mm.
of folks who are super curious and like, oh wow, a bit like you back in the day when you were like, oh, what's this kind of weird
Yeah,
wonderful
yeah.
thing? So people are probably curious, like they're going to be coming to you, they're going to be looking to understand how can it benefit us. Kind of the roles, I mean, pros and cons. Do you have a preference, or?
I don't have a preference. They're just kind of different, right? I guess it's sort of like it. Well, it was a job change, right? So sometimes you just go from one company to another company. The role or the vibe is a bit different, and that's okay. You can enjoy both. And I think, like you mentioned, especially in the large financial organization, one thing I really enjoy about my job now is there's certainly an education element. So people are asking you about it. They've heard about quantum computing. They're trying to think, oh, who in the bank is looking into this? And then eventually somehow my name gets to them. So then I end up having these conversations with people from all different parts of the organization. And I remember one time last year we were able to give a sort of educational session to the group MT and the board as well, which was very exciting. So I was able to
Amazing,
explain
yeah.
to them, yeah, because when you get that level of interest, it sort of like invigorates you just in a different way to being able to do a bit of everything in a startup, right? So it's just, I guess it's a different kind of excitement and a different kind of enjoyment from the job. It's more of a education role as well as a sort of software development role at the moment, which is a bit, yeah. I still get the variety, which is fun, which is what I like.
Exactly, and given kind of how hard you've studied and kind of where you are on your journey, it's you're well placed, and it must be quite nice knowing that you are genuinely that kind of subject matter expert within a very large kind of company, global business. So yeah, that's got to be super satisfying. I guess we mentioned QC's in its infancy, certainly within financial services. But I guess, in your opinion, how do you see quantum algorithms affecting technology, not only, I guess, within financial services, but generally wider industry sectors as a whole?
Yeah, no, that's a good question. So for quantum computing specifically, I mean, you can go a bit broader. So you can sort of say you have quantum technology as a broad scope, and then you can have almost people say there's sort of 3 subsections to that. There's like quantum computing, which is mainly what I'm focused with, quantum security, which people in the bank have asked me about, but I don't deal with directly, and quantum sensing, which is something I personally, in my role in financial services, don't deal with much, but is still a very important technology area. So the security one is an important aspect because that will affect everybody in every organization. So there's an algorithm that people may or may not have come across before called Shaw's algorithm. And at its nuts and bolts, what it does is it's able to do an operation where you take two very large prime numbers, you multiply them together, and you have the result. But what it's able to do is, if you have the result, it finds out what the two numbers were originally, which is very difficult to do on a normal computer. Even like if you had a super large, biggest supercomputer in the world, it'd still take, I'm not talking millennia to solve, if not longer. Whereas a quantum computer can, in theory, do that in reverse. And why that's an important problem is because that's how some encryption algorithms work. They take advantage of the fact that that problem is difficult and assume that no computer will be able to do it. But now a quantum computer is able to do it. You've got to start thinking, okay, I need new ways to start building these encryption algorithms. And a lot of institutions around the world are sort of looking at that now, or what's called PQE, or post-quantum encryption. There's an organization called NIST, which is the parallel to MPL, where I did my PhD, but in the US, and they've just recently published, I say recently, last year, published their up-to-date standards on what you should be doing for quantum security. And then going back to the sort of the other pillar, what I'm focused on in quantum computing, there's lots of applications there as well, where you have quantum simulation. So if you're in the pharmaceutical industry, for example, it's difficult to simulate a molecule because molecules are themselves inherently quantum. They behave in a quantum way, right? You can put that behavior on a quantum computer quite easily because you get that behavior for free because it is behaving in the same way. So that's one advantage that you can get. And then obviously what we're looking at now is things like optimization problems or machine learning and AI problems as well, because you can exploit this potentially much larger information space you get from using qubits in a quantum computer than you would on classical. So I was talking to someone about this yesterday, and I think a good sort of rule of thumb that you can sort of think of how much larger this information space is that in a classical computer, when you have a bit, every time you add a new bit, you have 2n, where n is the number of bits. So you almost double because you've got the two states, 0 and 1. Whereas for a quantum computer, it goes 2 to the power n. So every time you add a quantum bit, you double your information space. So that gets exponentially larger every single time. So by exploiting that property, you hopefully are able to create algorithms that can just solve certain problems in a much more exponentially powerful way that current computers can't. So that's what gets it very exciting. That's what's hopefully going to push the technology sector forward as well.
Amazing. And obviously, QC is, I guess, potentially going to change kind of the norm, if you like. I mean, can you put a kind of finger on how long that process may take before we start actually
Yeah.
seeing this in the real world? Or
No, that's a really good question. I think there's people typically say, that the easy answer is like, it's 10 years away. It's 10 years away. But I feel like people have been saying that for a few years. But there's been a few announcements recently, especially from like big tech companies like Microsoft, Google, IBM, where they're really making a lot of advancements in their quantum technology programs. But I think it's going to be a bit of a staggered approach, because I would say from our conversation a minute ago, quantum security is likely to be the sort of first beneficiaries sector. That's a bit more developed. Then I think it's going to be quantum computing. Then I think it's going to be these algorithms that we hope to get some true advantage of. So I think it's between 5 and 10 years away before we start seeing what's called a truly fault tolerant, where you see true useful advantage from a quantum computer. That's where we can mitigate all the errors and the noise that you see in a quantum computer, and still be able to run long enough algorithms that you get a meaningful result out of it. So I would say before we get to that stage, between 5 and 10 years, I think is an optimistic outlook. And I think it's well within reach, because the technology moves so fast. There seems to be a new announcement every 2 to 3 months on some advantage or some development that some company or research group has made to sort of further advance how we build a quantum computer, or how we mitigate against these errors and noise that we experience when we do these algorithms and these computations. So that's my 2 cents, but hopefully it'll be quicker.
yeah, fingers crossed. You mentioned it at the beginning. Obviously, QC is on its journey. What's being done in relation to improving kind of qubit stability and error correction within QC?
Yeah, that's very, very good points. That's the sort of main, I guess, engineering hurdle. And there's 2 aspects to that. There's the hardware aspect and the software aspect. So the hardware aspect is you've got to think of ways that you build more robust qubits. That can come down to having better isolated environments for your qubits, or that can come to down to how you sort of design the actual qubits themselves and how you connect them in some sort of way. And basically, you want to mitigate what are called sort of like loss channels. Essentially, you want to reduce them as much as possible and keep them well isolated, and have them only interact with the signals that you're inputting and outputting as well. So that's sort of one aspect of improving the hardware to making sure that's as robust as it possibly can be. And then the other aspect is there's a whole software, effectively research side around quantum error correction, which is a huge field, very complex. And that is essentially trying to say, okay, we have some sort of noise and we know that the qubits may decohere or have a bit flip at some point in the calculation. How do we put code on top of that can account for those errors and mitigate in software the response that we're getting? And this is where you may hear these terms called like you have physical qubits and logical qubits. The physical qubit is the individual device that you have that's tiny, it's microscopic on your chip, or it's an individual atom or ion, depending on how you build your quantum computer. But you can add more around them, sort of ancillary qubits, to create what's called a logical qubit. And that is essentially a bunch of qubits acting as if it was one, where if one falls over or one has an error or some sort of like phase flip or bit flip, the others can pick up the slack almost. And then it's how you build those error correction codes on top of these sort of logical qubits as well. So there's a lot of push in big tech companies to create a really solid logical qubit. I think the best known example I have to see this is IBM. They've been building quantum computers for years now, and they published their roadmap. And I can't remember the numbers exactly, but they're saying they want to get to a certain number of physical qubits by 2030, say, but what seems like a lower number of logical qubits, but they'll be much more stable and much more robust to do more interesting calculations with. So it's sort of two-horse race in the sort of bringing the two software and hardware sides together so that you can really build that in that true fault tolerance is what it's called in the industry as well.
Yeah,
And
so
it's not an easy problem to solve.
I was going to say, but I'm assuming that is fairly crucial, obviously, in the development of QC and actually seeing it in anger, kind of in
Oh,
the
100%.
industry. Yeah,
Absolutely, yeah. Because it's when you start seeing this fault tolerance is when you can start building these useful algorithms that can be applied to, like we mentioned earlier, the pharmaceutical industry or what we work on now in the financial industry. By having these, when you have these truly fault tolerant quantum computers, that's when you're going to start really seeing a game changing move. And we always talk about quantum computing will one day have its chat GPT moment, right, where it will be suddenly in the public's imagination and suddenly everyone will care about it. So it will be around the time we can crack this fault tolerance with a quantum computer.
yeah, you can't really fathom how powerful potentially that could be, right? And how it could not only change certain industries, but I guess us affect us, the normal person day to day.
Yeah,
Everybody's using
absolutely.
kind of AI, whether it's on your desktop or using it for, I don't know, for delivering something to a client, and everything in between. So, yeah, I mean, God knows how powerful that could be, right? It's scary. So,
Yeah, it is scary, and I think a lot of discussion around this goes into sort of like regulation and ethics as well. So I think a lot of the regulators are sort of doing their fact-finding missions at the moment to try and understand the technology better, so they can regulate it so it stays safe and is used for the greater good than it otherwise would be, and make sure that they understand the technology as well. So I think it's a very crucial point.
yeah, so I guess that segues quite nicely into, I guess, AI, ML. In your opinion, how can quantum computing potentially revolutionize AI and ML? Yeah,
Yeah, no, it's a very very good point. It's what we spend a lot of our time working on currently. It's my employer as well. So there's two main ways that we would potentially see advantage in like AI and ML, and the first could be a speed advantage. So maybe you're able to train faster, or maybe you're able to get a result from your pre-trained algorithm faster if you want to, I don't know, do some sort of classification task or sort of prediction task, whatever that may be. And on the other side, what we're also seeing early signs of, and we need to explore a little bit further, is that we're seeing that we can potentially train algorithms or get our quantum algorithms to a similar level of, say, accuracy, precision, or whatever your metric is of performance, but being able to train on less data than you otherwise would for classical computers, because you have potentially this much larger information space. available to you from a quantum computer. So that's the sort of two main ways we're potentially seeing advantage slowly coming from quantum computing at the minute. Obviously, the hardware, as we were discussing earlier, is still at this earlier stage. So we're sort of trying to increment where we can gain value now and gain sort of insights now to then build a sort of understanding that is ready for this moment of fault tolerance that will happen with quantum computing.
Awesome. Well, yeah, I mean that's super insightful, and I'd like to think any, I guess, rising stars within the QC world who may be tuning into this would hopefully have taken a couple of key pointers. Obviously, listening to your journey. So, if anyone does want to reach out, Shaun, directly, I guess LinkedIn's a good platform
Yeah,
to.
absolutely. I'm on LinkedIn. I post on
Yeah.
that every now and then. We'll probably post this podcast on LinkedIn, so that'd be great.
Yeah.
Yeah, absolutely. That's the best way to get in touch.
Yeah, awesome. Well, absolute pleasure. Yeah, really appreciate your time, and thanks for coming on. And yeah, hopefully we can do this again sometime soon.
No, I hope so. It was really good. You asked some great questions, actually, and I think questions that are often asked, but also often not asked. So you need to get that full sort of encompassing picture, which is exciting to talk about.
Appreciate it, Shaun. Thanks so much.
Thank you very much, Zach. I'll speak to you later.